All right, so that's where we stopped yesterday. Directional derivative. It's a very simple subject. It's just some very straightforward implication of chain rule. That this is a slide which explains what it is. It's just when we increment the function in a particular direction and we ask what the rate of change of that increment is. I said I'm recording everything. Just double check that I'm recording. Yes, I am recording. With the help of a chain rule, that's the second slide we saw yesterday, we developed this formula right in here for the directional derivative via the gradient vector and this u vector, u hat vector, which delivers the direction. I just emphasize this again, when you use these computations, you have to make sure that your u vector is unital. Otherwise, the magnitude of that vector will influence the result, and you will end up with the wrong rate of change. We also saw this slide where we use the Cauchy-Schwarz to present some control, some estimate on the rate of change. The typo from yesterday is still present. Somehow I fixed it, but apparently the update didn't get through to my files. I'll double check this later. So if you want to control the rate of change of the function, if you want to control the value, absolute value, it's a number here on the left-hand side of your directional derivative, you can use Cauchy-Schwarz, and then you will control it with the magnitude of the gradient. So your rate of change will never exceed the magnitude of the gradient. There are two distinguished directions in which the rate of change actually exactly as the gradient. That's the direction in line with the gradient. It's said right here in these two bullet points. Along the direction of the gradient, you will have the rate of change which is exactly as the magnitude of the gradient. In the opposite direction, you will have the rate of change the same in absolute terms, but it will be actually negative rate of change. It will be decay rather than, it will be decreasing rather than increasing. There's another distinguished direction which is determined by the gradient, the perpendicular direction. It also represents some interest. It's a direction in which you don't have any change. Because when you're perpendicular, your dot product formula delivers 0 and your rate of change is 0. That's a diagram we saw yesterday. The shape here looks like a semi-sphere. In general, it works every time. For any graph. So in the direction of the quickest ascent, that's the direction which is pointed by the gradient. The direction of the quickest descent, that's the direction which is pointed by the opposite of the gradient, right here in the bottom on these level curves. And the perpendicular direction, it's a direction where you don't have any change. And that is also the direction where the level curve goes. Because level curve, it's the one where a function keeps the same value. So along the level curve, function doesn't change. That's why along the level curve, whichever shape that is, not necessarily a circle, your rate of change will be 0, and that's why you can use the gradient. You can use this logic in the opposite direction. You can use the gradient to predict the direction of the level curve. And the direction here can be replaced with a tangent line, as a matter of fact. So that is exactly the example that's the example which explains this behavior. This time we have that's the function. If you plot this in GNU plot, that will be circular paraboloid or paraboloid of revolution. We did it actually with you. I did this in class with GNU plot. I plotted this paraboloid of revolution. The gradient of this function, part A, that's the gradient, two partial derivatives by x, with respect to the x and with respect to the y. Level curves, these are the concentric circles, right? If you just equate this function to, actually we plotted this as well with the GNU plot, these concentric circles. Yes, that's right. So the gradient at every point, it points perpendicular to the level curves, and the direction of the gradient shows you the direction of the highest ascent. Because we're looking at this paraboloid of revolution, the ascent goes away from the origin. That's why the gradient pointing away from the origin. That's another instance of the gradient at other point. So for different points, this vector will deliver different directions, but every time it will be the direction of the quickest ascent, and every time it will be a direction perpendicular to the level curve. Yeah, this is all there is to this function. It's another example, just on one slide. Very simple computational example. Find directional derivative of the function f in a direction of a vector 5, 1 at the point 2, 1. And that's the function we have to consider. For this function, probably we don't know the shape. Yeah, x cubed plus 2y squared. It's hard to predict the shape, but it will be close. It will be some sort of it's not a paraboloid. Actually, no, I'm sorry. No, it's not going to be like that because x cubed it has negative values as well, so your graph will go down as well. Yeah, but if you want to see the shape, you need to use the plotting software for that. If you want to see the detailed shape, but computationally, we don't need to know that. We have all the formulae to finish these computations. We compute the gradient right here. Two partial derivatives with x and with y. The numerical gradient at particular point of interest, 2, 1. Which is substitution. Direction, we always take a unital version of the direction because we don't want the magnitude to influence the computation. That's why we normalize the vector u. So we take u hat and we divide by the length. You see root 26, that's the length of this vector, 5, 1. And that's the computation. And that's the end of it. Any questions? Most of the time, the questions in relation to directional derivative will be of this level of difficulty. Very easygoing questions. They may be wrapped in some sort of plain English type of questions, like find the direction of the quickest ascent to the hill, which is shaped as a graph of this function or something like this. But most of the time, it will be like that. I'll show you one more involved example with the directional derivatives. I like this example for another reason as well, because it has some connections with the first year linear algebra, and I want to show you that. I have to go to my other slides, and I realized I didn't set that because I forgot about this. I just remembered this example just now, so I'll take just a few seconds to set that up. Let's just go back to the desktop. I need the terminal to set the, yes. Too many yeses. Yes. I need to set this up, and I need this. Full screen, resize. Here's my file. Yeah, directional derivative example, I call it. That's the example I'd like to discuss with you. No, move. Yes, here it is. So we have now not one vector, but 3 vectors, u1, u2, u3. And we given that this is the orthonormal system. How many people in this class remembers what the orthonormal system is from the first year? It's good. It's a good rate of memory performance. Basically, it's explained right here. Normal means that all the vectors are unital, which is what we need when we discuss your directional derivatives. And ortho, this prefix ortho, means that they are pairwise perpendicular, and that is right here by the dot product like so. Right. So the example which I'd like to show you with the directional derivatives is this example. Look at this. Show that if you compute the sum of the squares of the directional derivatives with respect to these 3 vectors from the orthonormal system, so this time we're looking at 1 directional derivative, like in my previous example, but 3 together. 3 vectors, 3 directional derivatives in pairwise perpendicular directions. All of these symbols individually, they are numbers, right? They're not fruits. We discussed this yesterday. You can sum them up as squares. It will be another number. What I claim is, or what the example claim is, it will be the same if you take the sum of the squares of the Cartesian derivatives, x, y, z derivatives, which is in another language, the magnitude of the gradient, right? Because the gradient is something which consists of these pieces as components. That's the coordinates of my gradient. So this is it. So we need to equate these three directional derivatives to the Cartesian ones. Here's just a reminder what the gradient is. Nabla f is that's the vector with these components. Right. So I'm going to use this result. The only result we know, the only result we need to know about the directional derivatives, how to compute them via the dot product. So this is the result. This is this result used 3 times for the u1 direction. You see, rate of change in u1 direction, dot product of these two. In u2 direction, again, rate of change of vector in u2 direction, and in u3 direction. I just use the same result 3 times, 1, 2, 3, for different vectors. Right. After you know this, the finish of the solution actually, it just involves one result from the first year. Some of you may remember that. Some of you may not remember that. It's certainly in the tutorial book for the first year, 100%. I'll just open the result and I'll ask you how many people remembers the number of that question in the tutorial book. That's why your performance probably will fail you, right? To remember the performance. Well, at least maybe you recognize it without the number. Look at this. So I'll call this lemma. I just frame it as a lemma. So look what it says. The result says this: if you have any vector in R3, any vector, no matter which one, it has not. Some already remembers the result just for these two things. So the result itself has nothing to do with the gradients or calculus. It's just a vector result about the vectors. So if you have any vector from R3, then the result says this: the magnitude of this vector, which we know how to compute it, right? It's sum of the squares of the components. But you also can compute it like this value. You take dot product of this vector with these 3 elements of your orthonormal system. You end up with numbers. You square them, sum them, and that's the magnitude square. How many people remember this result from the first year? That's good. That's good. Do you remember the proof of that result? You don't. It's a very short and very beautiful proof, actually. We can swap. We can just. No, that's right. That's so fine. If you remember something, it's good. I'll show you my version. It may click with yours, or maybe you have something else. It's all. I mean, probably you can come up with a few different ways to prove it. So look at the proof of the lemma. If you believe in this lemma, if you just reference this result from the first year, and for instance, if you persistent enough and you find this result in the yellow book, you find a number, then you can say, by that number, I can just finish the question straight away. Because look at this. If I use this lemma for the gradient vector, if you just replace the gradient vector here on the left-hand side, this right-hand side will be this value, right? Dot product, and dot product. So this lemma is this connecting element which links this value to this value. And if you remember the number from the yellow book unfortunately doesn't have an index, I think, does it? So it's harder to find this question, but with some effort, probably you can. If you reference that, that will be quite a complete solution. But here's the proof. The proof is nice. The main claim which we need to remember from the first year is that orthonormal system, and U1, U2, U3, it's my orthonormal system. It's the one which also a basis. It was another question in the yellow book. There was such a question, I clearly remember that, though I don't remember the number. This is a basis. And because it is a basis, every vector can be represented as a linear combination of the elements of this basis. Oh, no, what did I do? Sorry. Hence, X is a linear combination of these vectors with some maybe unknown, I mean, we don't know them, with some numbers. In general, when you try to figure out those numbers, if you have any basis, and you did this quite a few times in the first year, probably you're now bored to death, when you were bored to death with these sort of things, you have to use the Gaussian elimination, all of these systems, you need to solve them to find this x1, x2, and x3. But when you look at the orthonormal system, finding such representation, finding these numbers x1, x2, x3, is just, you can do it by direct formula. That's how you do it. Look at this. Furthermore, actually two things I have to show you now. On one hand, if you compute the magnitude of your vector, this vector, which is given by this formula, magnitude is a dot product of x with itself. If you replace x with this right-hand side, that's a replacement. And if you do the expansion with the dot products, you can do regular expansions as with the normal product. When you do the expansions, you can cancel lots of things. Actually, lots of things will be zeros. Every time you dot product u vector in the left factor with the u vector in the right factor, every time the indices are not identical, the product will be zero. That's the orthogonality of the system. And all those terms, they will disappear. All the terms where you product the u vector on the left-hand side with the same vector, with the same u vector on the right-hand side, only those products will stay, and those products, so only those products stay when you dot product u on one side with the same u on the in the second factor. Numerical coefficients obviously will be squared in that case. All the rest will just disappear. It's a step which is hidden by these dots. And then, because you also have this, because the system is also normal, these dot products, they are just the magnitudes, the lengths of your vectors, which are 1 all the time, and you end up with well-known Cartesian expression for the magnitude of the vector. Actually, that's a wrong comment. Forget about the Cartesian. These are not the components of the vector. x1, x2, they are not components like in the vector. They are the coefficients in this representation. So even though it looks like the Cartesian formula, it's not. These are the sum of these coefficients with respect to the orthonormal system. It's one thing that I note. And the second thing I note, on the other hand, if you take the dot product of x with u1, again, if you use this piece on the right-hand side in this representation, if you sub it in, you will have something like this. And when you do the expansion again, here, when you do the expansion, every time you dot product u with u1 on this side, it will be 0 as long as you're not taking u1 in the first factor. But when you taking u1 on the left-hand side, it will be 1. For the same reason it is 1 here. That's why it is x1. And that's the beauty of dealing with the orthonormal systems. In general, when you have a basis which is not orthonormal, finding these coefficients, it's not an easy task. I mean, it's a very, very algorithmic task, but still it's a lengthy task with the Gaussian elimination and solving of system of linear equations. In case you're looking at the orthonormal system, here, direct formula. Dot product delivers first x1. Similar dot product, and I'm hiding the same piece by dots here, delivers x2. And the final dot product delivers x3. And that's the finish of the lemma, because here, on one hand, the magnitude of your x is sum of the squares of x1, x2, x3. On the other hand, x1 and x2 and x3 individually, they're given by these dot products. So that's why you have this right-hand side in here. That's the proof of this lemma, which was framed as a question in the first year. This is just a quick refreshment what happens with that. And now if you use this lemma back to my original question, if you use this lemma with my original question, this identity, that will finish the proof of that identity. If you're still copying, that's the end of the proof. Any questions? It's a nice, I mean, I was trying to find not a straightforward, not just the elementary computational example with the directional derivatives. That's the one I found. It's a good one. There's another one I found. I'll put it in the tutorial question. It's also a nice one. I wonder if you can do that. Well, you'll see, obviously, it will stand out from the rest of the boring computational questions. Yeah, so there will be this one, and there will be another one. It will be marked with H, so it's like, if you like challenges, you can attempt that. I'm not sure if your tutors will attempt this in class, but it's not up to me to decide. Right, so the second subject we need to discuss today, it's back to tangent planes. We discussed it a little bit when we discussed these O notations and the affine approximations to differentiable functions. Now we're going to discuss the tangent planes or tangent lines with the help of what we just know about the gradient. That the gradient actually is something which is always perpendicular to the level curve or level surface in case you go higher dimensions. And that gives you another opportunity to find these tangent planes. It's another computational subject, as long as you know this main principle. The rest is easy, but I'll show you a few examples. Let's just go back to, yeah, that's the one, that's this file. It's the one, again, put by Jonathan Kress. So we'll just read through this. Right. So this time we're going to look at at surfaces no longer as graphs of functions, but as level surfaces. So as a set of points which are solutions to some sort of equation of this type. Equation of three variables, x, y, z. This equation, most of the time it delivers a surface in space. And for the surface, we need to know, well, we're going to discuss how to find a tangent plane to that surface. And this line basically explains that. It says, well, it says this. If you take, and it's like a sort of indicative explanation why this works. It's not really a proof. Another indication of why this works, it came from our discussion of the directional derivatives and this distinguished direction perpendicular to the gradient. That's another indication that this should work. So look what it says. If you take any curve on a surface like that, if you take any curve on a surface which is given by an equation, abstract curve, that curve will have some parametrization. And let's just imagine we have such a parametrization. So because the curve is assumed to be on a surface, if you sub it into the equation of a surface, it should work. Yes. If you sub it in, like this, into the equation, this should work for any t. You should end up with the correct identity for any t. On the other hand, if you use the chain rule, if you differentiate this piece by t, that's another instance where you can use the chain rule on the left-hand side. On the right-hand side, that will be 0. That's the chain rule used, you see. So you look at this piece as a composition of two functions, phi and r. You differentiate, this is a chain rule, in matrix form. And now you make the observation that the first factor here is just a gradient, and the second factor here, it's this vector which we know geometrically gives us the tangent vector to the curve we chose on my surface. So the line basically says that if you take a surface on the curve, no matter which curve you take, no, the other way around. If you take the curve on the surface, then the gradient will always be perpendicular to that curve. It's not something we saw on the level curves. Gradient was perpendicular to the level curve. When you take level surface, gradient perpendicular to every curve on the level surface, that's why it's perpendicular to the surface itself. And that's what it said right here. And we can use this observation to actually find this tangent plane to the surface, to the level surface at any point. Here's the example. That's the surface we all know, right? So this is the surface we know it's a sphere, but it's a level surface because it's given in this form. So it's a sphere. We can ask how, well, the question, yeah, the surface is, you can just introduce this function phi on the left-hand side. Your constant c will be 6. So if you want to find the tangent, so the normal vector to your sphere, all you have to do, you have to take the gradient like this, and that will be all you need. So if you want to reconstruct the tangent plane, because you know already the normal to that tangent plane, here it is, at this particular point, numerically, if you take it, that's the numerical evaluation. If you know if you know the normal vector, reconstruct the plane itself perpendicular to that vector. We have a direct formula in 3D, right? Well, that's the formula. You just take this. You take these coefficients you come up with, 2, 4, and negative 2, as factors in front of x, y, and z, right in here. And then you choose the right-hand side in a way that when you plug the point at which you want to find the tangent plane, when you plug this point in the left-hand side, you end up with the correct identity. So if you take this 1, 2, negative 1, you cross the left-hand side, it will be exactly 12. That's how the 12 on the right-hand side came up. Yeah. Again, it's a very straightforward example. Very good for the Friday discussion. Tangent line. The same logic works for the tangent line. It's because, again, when you want to predict a tangent line to a level curve, that's a level curve. It's ellipse, we know it. It's an implicit equation of an ellipse, but we can think of it as a level curve. If I'd like to predict a tangent line to this level curve, I can use the same principle. Gradient is something which is perpendicular to the level curve. So I compute the gradient of the left-hand side. So here's my function phi. That's the function phi I take. My ellipse becomes the level curve given by this equation. Gradient 6x for y numerically at the point of interest. That's the point of interest. It's just this value, 12, 4. And that is a vector perpendicular to my line level curve and in the tangent line to the level curve at the point 2, 1. So again, we know how to construct the left-hand side. We take these coefficients 12 and 4 on the left-hand side. And then we just compute the right-hand side in a way that this point 2, 1 becomes a solution to this equation. So if you put 2 and 1 in here, that will deliver you 28. That's how 28 came out. So again, straightforward computational equation. This slide also says you can try to do it by the first year method when you directly solve for half of the ellipse. I mean, if you solve this implicit equation for y, you will end up with 2 solutions, right? One of them will be this solution right in here, root 7 take 3 halves of x squared. That will be the solution which is the upper arc. So upper arc, sorry, of your ellipse. If you take with negative, it will be lower arc of your ellipse. But because your point 2, 1 is on the upper arc, you take this only one solution. And for this function, because now the graph, this upper arc of the ellipse is given by the graph, is a graph of a direct given, explicitly given function. That's how you should say it. You have a first year method to find this tangent. You can try. I assure you that you will come up with the same equation. But that's boring. Well, you can try. Why not? Doing boring stuff is also some sort of good exercise. You just discipline yourself and everything. Any questions? Just see what else we have in here. I think the rest of this set is just examples, all about the tangent planes and tangent lines via gradient. So that's another one. So here's my surface. We saw the surface before, by the way. I mean, before it was z equal x cubed plus 2y squared, if you remember. Yeah, it was in one of the examples on directional derivatives. It was a function z equal x cubed plus 2y squared. Now you just transform you change the view on that graph. Now you move your z on the left-hand side, and now you can think of that graph as a level surface. It's a good move. I mean, it's a good trick. As a matter of fact, you can always change the view on graph of a function in 3D, of a graph, the view on the graph of function of 2 variables. You can always change it to a level surface by moving your z variable on the left-hand side and making it an equation. It very often pays off. So it's the same graph. So we'll look what we have to do. At the point, that's the point, and that's the point on that graph. We can check this. If you take this now as 2, 1, 10, you take it across here, it should work out. It should work correctly. So 2 cubed, it's 8, plus 2 take 10 is 0. It works. So it's a point on this graph, or on this level surface. We need to find the parametric equation of the normal line and Cartesian equation of the tangent plane. It's all just linked to the gradient, because the gradient is something which delivers the direction of the normal to the tangent. As soon as we know the gradient, we can come up both with the parametric equation and the tangent plane. It's all here. So I take my function for the left-hand side, phi. I compute the gradient. Here it is. That's the gradient right in here. Numeric, I mean, it's a formula for the gradient at the point of interest. That's the point of interest. If you just plug these values, that's a numerical value for the gradient. And that's all we need to finish the equation, because if you want to see the parametric equation of the normal line, here it is. You take the direction of the gradient, and you take the point for the position. And that's the parametric equation for the normal line. Tangent plane, that's the same logic we used 2 slides ago. You take the coefficients of the gradient next to x, y, and z, right in here. 12, 4, 1, they came from here. 12, 4, 1. And you come up with the number 18 in such a way, I mean, you pick up a number such that if you take the point at which you construct your tangent plane, if you plug it in the left-hand side, you will end up with the number on the right-hand side. You test it to 110. It's 24 plus 1, 28. Take 10, it's 18. That's the one. And that's all there is to it. Very straightforward equation. Just test your understanding of the gradient and nothing else. Next one. Find the best affine approximation. It's just this is a slide which actually now links our previous approach to the tangent plane with the approach on the slide before. So before, look at this. We found the tangent plane. Here it is. This level surface at this point. If you keep this in mind, and then now I flip the slide, it's the same function. Look at this. But now my surface given explicitly, z variable, which is f of xy, now kept aside on one side and the function on the other side. And we need to find the best affine approximation, which, if you remember the terminology, this is again that tangent plane we're looking for. It's just the knowledge of terminology here, which maybe you don't have yet, but you'll remember it eventually. This best affine approximation, that's the same tangent plane with probably minor cosmetic difference when you represent the equation for that tangent plane as an explicit function. So it should be y equal, not like implicit form like this. I mean z equals, sorry, not y, z, because z is the dependent variable. So that's what we do. Look at this. Well, directly, this sort of questions, when we do this question, when you do this sort of questions directly, you have to go after the you have to differentiate that function, this function. So I differentiate. That's another gradient, but this is a gradient of the two-dimensional function. Here it is. You take this gradient at the point 2, 1. That's the two first components of the 2, 1, 10. Yeah, that's the best affine approximation. That's the formula for the best affine approximation. We knew from our discussion of differentiation. It's a value of the function at the point of interest, gradient, dot product with the increment. If you do the computations, look what you end up with. Negative 18 plus 12x plus 4y. Take a picture of this line. Imagine here you got z equal negative 18 plus 12x plus 4y. I flip back on the slide before. Oh, I need to press this button. Here. If you solve this for z, it will be the formula we just found on the other slide. You need to make an effort and understand these two different looks, two different approaches to the tangent plane. You have to have a very clear picture of these two different approaches. It's not a difficult effort, but you have to make this effort. On one hand, we do it directly via the affine approximation. On the other, we do it via level surfaces and gradients and tangent planes to these level surfaces. Yeah. These two lines are already present on the slide, so I didn't need to flip it back. Instead, I should have put the forward button once, press the forward button once. It's the same thing. Right. Another example. It's the same surface, by the way, which is just development of the same example. Look at this, the same level surface, or the same graph, right in here. Now the slide suggests we make two cuts, two vertical cuts, one with plane x equal 2, so one way, and then with the plane y equal 1, this way. Number 2 and number 1, they're not accidental. They, again, because they all, both of these planes, they go through the same point, 2, 1. So we're just spinning our example around the same point, 2, 1 or 2, 1, 10, if you're on the three-dimensional position of that point, 2, 1 on the xy plane, 2, 1, 10 in space. Now look what we have to do. Find the tangent vectors to these curves. So when you cut through your surface, you will end up with some curve in the intersection, two curves. We need to find the tangent vectors to those curves. And then by considering those tangent vectors, provide a parametric equation for the same tangent plane. We found two different ways already. Let's just try to do that. So if I need to find the tangent vectors to the curves, I need to present the parametrization to those curves. Look what the choice of a parametrization on this slide suggests. First one, x equal 2, that's why 2 in the first component. For y, which is take parameter t, this one comes from the solution. This expression comes from here if you solve for z and if you replace x with 2. If you do that, that will be the value right here. Well, t plays the role of y. Same parameterization for the other cut, for the y equal 1 cut. Now this time x is a parameter, t, y is 1, because that's where we did the cut, our cut. And that's a solution again, right from here you solve for z, but this time x is t, y is 1. That's a solution. Two parameterization of these two intersections. We know how to find tangent vectors to parameterize curves. It's just a derivative. Here they are. We don't care about these derivatives in general. We need the derivatives at particular point where this curve's passing through the 2, 1 point. So we take particular values for t on both instances. Here we take t value 1, right? Because that's when this curve hits the point 2, 1, 10. And here we take the value 2. If you take those values, right in here actually they said, that's the numerical values for the tangent vectors to my curves. And that's why the parametric equation for my tangent plane is this one. That's the way how we construct plane parametrically. We take the position point, which is 2, 1, 10, the same point in space, and then two directional vectors, which came from the tangents of my two curves. The same tangent plane now in parametric form. Do you remember the method how to convert parametric equation of a plane into Cartesian equation of a plane? What does the method say? What you have to do to convert the parametric equation of a plane into the Cartesian? I'm asking because I forgot myself. Huh? Cross product. I mean, you do the cross product to find a normal vector, and then you follow the procedure from before. Yes, you can do that. Any other way? Do we know any other way besides cross product? You don't? Because now I remember the second way. You can, you know what you can do? You can solve for x, y. Wait a second. What did I say? Right. Well, the method, there is another method, and actually that's the one that is more in line of the first year stuff. Cross product is a good one. The other one is, I'll try to explain it verbal. I don't have any slides to explain that. I mean, written slides to explain that. You take this parametric form. You take this parametric form. You write it up in component way. So your R vector on the left-hand side, it's x, y, z. Right, so you write up these component equations. X equal, right-hand side, first component. Y equal, right-hand side, second component. Z equal, right-hand side, third component. And then you take any two equations, say first two, and you treat them as two equations with two unknowns, t and s. You can solve them. When you solve them, your solution will be in terms of x and y, your right-hand side. And then you sub on into the third expression, and you will end up with the pure xyz thing. And that will be your Cartesian equation. That's the other way to do it. Basically, you have these three equations with two unknowns. You use 2 to get rid of t and s in the third one. If you do that with this one, you will come up with the same Cartesian we found in the other two approaches. Yeah. Another example. Another function, another level curve, right in here. This time we call it S2. There are a bunch of questions we have to discuss with you in relation to this. Describe S2. Show that S2 touches S1. S1 is from the slide before. Touches S1 tangentially at 2, 1, 10. And that means that they both pass through the point 2, 1, 10. And the tangent lines, tangent surfaces to these two, S1 and S2, they are identical. That's what it means, touches S1 tangentially. Solve g, x, y, z for z in terms of x and y, near 1 to 1. And we can do that. Find the best affine approximation. What fact involving makes it possible to find g? Let's just try to see what we have, what sort of answers we have for this. Describe S2. Do you know how to describe S2? Can you see from the way S2 is written, can you see what the shape geometrically will be? Of course you see, because you have like the printouts of the notes, right? Ah, no, you don't have a printout. Well, but probably some of you have the printouts of the Jonathan Kress from 2014. And if you keep track, probably you know it. It should be a sphere. It will be ellipse if you have different factors next to the squares. But this time next to the squares we have 3, 3, and 3, which means it's a equally scaled ellipse, which means it's a sphere. So you can see this by extracting perfect square, by building this perfect square as components. I think it's done on this slide. Yeah, right in here. I mean, the steps are missing. Arithmetic steps are missing. But the actual trick of building a perfect square from an expression of this type, well, I presume you know this trick. So if you do this trick 3 times for x, for y, and for z, you will end up with this expression, and that is the equation of a sphere. You got the center, 4, 5 on 2, 59 on 6. Well, what can I say? 59 on 6. And then you got the radius. Well, it's not the radius because you have to divide by 3. But if you divide this by 3 and take a square root, that will be the radius right in here. So that is the sphere. For us, what's important is that this sphere passes through the same point as before. Actually, you don't need to do the perfect square to see that. If I flip back to my slide before, to see that, all you have to do, you have to take this point 2, 1, 10 and check this point against this equation. If it works, then your sphere passes through that point. So you don't have to extract the perfect square. You only need the perfect square to convince everyone else that this is a sphere. That's all you need it for. For the rest of the parts, you don't need actually the extraction. So, yeah, that's the verification. You see, if you first check that g 2, 1, 10 is 0, that's why it is 2. We previously found the normal vector to the first surface as 1, 12, 4, negative 1. If you do the same analysis for the second sphere, so you find the gradient of a second sphere, here it is. Somehow, you see, on this slide, when they compute the gradient for g, they use the perfect square version of the g, right? Because right from the computations, it's 6 and brackets and brackets and brackets. Again, it's a redundant step. You don't have to do that. You can use the original formula for g if you want to find the gradient. And that will deliver the same value. Is the gradient at the point, and you can see spot on that actually one gradient is a negative of the other gradient, which means even though they're pointing in a different direction, tangent planes will be identical. And that's all you need to produce to convince everyone that your surface is touching tangentially. Yeah, that's what it said in this last line. What was the third question? Who remembers? The third question was solve it for one of the solve it explicitly, and that's not an easy solution. That's where you need the perfect square extraction, because you see we use this perfect square. We move all of the terms with x and y on the other side, like this. Then we divide by 3, we take a square root, and we move this 5906 on the other side. It's a horrible business. I wouldn't recommend this doing anyone, even my worst enemy. You know? But well, if this on this slide it's required, that's how you do it. Well, the fourth part said find the best affine approximation, and that's actually the tricky thing. I mean, the question doesn't say do it via the direct method, doesn't it? So we can cheat a little bit, right? Because from our early experience, we know that this affine approximation should be the same as the tangent plane found via the gradient method, right? So if the question doesn't explicitly say do it via the direct method, which if it says would be real torture, because just finding the derivatives of the function like this, even Maple will probably suffer. Yeah, right. But if it doesn't, we can cheat, right? Because we know from the early experience it would be the same as before. So we can take that tangent plane, even though it's given implicitly, we can solve that tangent plane for z and present it as the affine approximation. Nobody would blame you for that. And I think that's exactly what is done on this slide. It is intentionally preserved. The function is, it's a good thing actually. The function is intentionally made so horrible to show you that this indirect way is better. Any questions? No? Well, it's the last slide. That's all I have to show today. Thank you very much. I'll see you all next week.